Good day, ladies and gentlemen. My name is Anwar Majid. I am Senior Geotechnical Engineer with the ECOM in Canada. Today, I'll be presenting challenging aspects of providing geotechnical baselines for microtunneling in difficult ground conditions in Calgary, Alberta. Co-authors for this presentation are Melanie Gray, who is Project Manager with the City of Calgary, Sean Pillai, who is currently Project Manager with the City of Calgary, and formerly he used to work with ECOM. Owner for this project is City of Calgary. AECOM was responsible for design and construction management. Ward and Burke Microtunneling was the tunneling contractor. I have arranged this presentation into few topics. First of all, I will provide brief overview of Englewood Sanitary Trunk Project and underground risks which are associated with such type of projects. Followed by that, I'll provide brief overview of microtunneling systems and geotechnical baseline reports for microtunneling projects. Then I will enter into specifics of Englewood Sanitary Trunk Project, and I will provide ground conditions that were encountered along the Englewood Sanitary Trunk alignment. Geotechnical baselines for the Englewood Sanitary Trunk that we provided, and at the end I will provide comparisons of actual ground conditions that were encountered during construction with the baselines that we provided. Why Englewood Sanitary Trunk was constructed? The reason is that the existing 15-street trunk that carries flows from North Calgary, Airdrie and Cochrane to the Bonnie Brook wastewater treatment plant is nearing its capacity, and Englewood Sanitary Trunk was constructed to provide additional capacity to meet current and projected wastewater needs. On this slide, this is basically a drone video of the project site. So I will run this video and I will provide some description of the project. The project was actually divided into two phases, phase 1 and phase 2. Phase 1 was approximately 3.7 kilometers and it was tied into the Bonnie Brook wastewater treatment plant. Starting from Bonnie Brook wastewater treatment plant, the first section is open cut and followed by microtunneling. So the microtunneling length was approximately 3.4 kilometer, and on the video you can see purple line is the open cut section. Red line is phase 1 microtunneling. Red circles are shafts which are used to launch and retrieve microtunneling boring machines. So microtunneling section for phase 1 was about 3.4 kilometer long and open cut was 265 meter long. Microtunneling size was 2400 millimeter and open cut was 1500 by 3000 millimeter box culvert. There were 9 shafts installed for this project and shaft shapes were mostly circular. 8 of them are circular, 1 of them was oval shaped. Circular shaft sizes varied from 8 meter to 11.5 meter in diameter, and oval shaft size was 11.5 meter by 8.5 meter, and shaft depths varied from 5 meter to 18 meter. You can see the tunnel alignment crosses several railways, major roads, and then a major portion of phase 1 was under major roads. Phase 2 is about 510 meter long and it is basically bore over crossing. Microtunneling was 510 meter. It means everything was done by microtunneling in phase 2 will be done by microtunneling. The tunnel section outside river was 2400 millimeter and under river we will be using two 1500 millimeter pipes. This means that we will use two types of machines, one size 2400 millimeter and the other with size of 1500 millimeter. So you can see here the phase 1 was connected to inner city trunk and phase 2, which is green line, this will be connected to West Memorial trunk connection, which is existing trunk. So West Memorial trunk connection or West Memorial trunk, it is 1800 millimeter in diameter. It will be connected to phase 2. So then phase 2 will carry flows from West Memorial trunk. Phase 1 will collect flows from inner city trunk, which is also existing sewer and 1800 millimeter diameter. And then phase 1 will carry flows from inner city trunk and phase 2, and everything will go into Bonnybrook wastewater treatment plant for treatment and final disposal into Borehole again. So there were 3 shafts for phase 2, all of them circular. Shaft size is 8 meter to 11.5 meter and shaft depth 7 meter to 14 meter. So you have seen that the tunnel section is very long. It is under river. It crosses major roads and buildings and railways. So we should expect variability in ground conditions along the tunnel alignment. And so if there is variability in ground condition, then the variability in ground condition that influence means, methods, and construction cost. And remember, there are underground surprises. We should expect those unforeseen conditions. And so that is a big risk. And that risk is shared between owner and contractor. So if there is change in ground condition, someone has to take the risk. And then risk is shared between owner and contractor based on what? Based on geotechnical baseline report that we'll discuss after this slide. So when we say underground risks, we have provided few examples of underground risks that we encountered on this project and some other projects as well. So boulders, that is a big risk. If you don't specify them properly, then that is a change in ground condition. And you can see here we encounter a boulder which was greater than 2 meter in size, and that was a claim that we had to pay. Frackouts can happen if TBM hits some unforeseen object. Okay, and because of that, the slurry that is used for microtunneling, that will come out of the ground. It is called hydrofracture too. It will break the ground, it will come out. And this slurry is under pressure, so it may damage infrastructure. So there were some claims on some projects with respect to frackouts too, and we had paid those. The other is nested cobbles and boulders, and this is very difficult ground conditions for microtunneling. If we encounter that, and if we have not baselined that, then that is another claim. Groundwater and high groundwater inflow rates, that is very important that we characterize this correctly and contractor knows about it. Sometimes we encounter aquifers, okay, and you see, for example, this is an example where we encountered aquifer, groundwater is coming out. This is 30-meter deep borehole. So we have to characterize that if there are any aquifers. Sometimes there are gas pockets in the ground as well, and we have to characterize gas because if there are gases in ground, we have to inform contractor. So if we are in difficult ground conditions and we have not baselined the ground conditions properly, so there could be damage to MTBM. Or if contractor has not brought the TBM according to baseline conditions, then TBM could be damaged. So then we have to decide who will pay that cost for repairing this TBM. So in this case, you can see TBM was damaged because of boulders. So they have to do emergency intervention and repair the MTBM. So now once we know the ground condition, then we have to select a microtunneling system. Okay, so there are basically 2 microtunneling systems, open face microtunneling boring machines and pressurized closed face microtunneling boring machines. Open face don't provide frontal support where they are open from front. They provide only lateral support, and they are good in dry soils, cohesive soils, and soft rock. Pressurized closed phase MTBMs, they provide both lateral and frontal support. They are suitable for all ground conditions. And basically, there are 2 types of pressurized closed phase: a slurry type microtunneling boring machine and earth pressure balance microtunneling boring machine. So which machine is good for which ground? Okay, so slurry machine is good for coarse granular soils, and earth pressure balance machine is good for fine grain soils. However, these, for example, the range of applicability of earth pressure balance machine is shown in blue, but it can be used in coarse granular soils with some soil conditioning. Similarly, slurry machine is good here. However, it can be used in this zone, but we have to do some soil conditioning, and we have to add some additives, polymers and other things. So now we will discuss a geotechnical baseline report starting from baseline from next slide. So what is geotechnical baseline report? It is a contract document. It provides set of realistic contractual assumptions, which are called baselines with respect to the anticipated ground conditions. So you see, we use word anticipated ground conditions, okay? It is an aid to administer the differing ground conditions. So if there are changes in ground conditions, baseline helps in those conditions. And it is a guidance document for bidding the project. So contractor will decide their means and methods and select a microtunneling boring machine based on geotechnical baseline report. It is a means to help manage the construction, and it provides fair basis for risk sharing between owner and contractor. So if ground conditions are worse than baselines, risk goes to owner, and if ground conditions are equal to or better than baselines, then risk goes to contractor. Baselines are two types: physical baselines and behavioral baselines. So physical baselines are the soil properties that we can measure in lab, or during drilling we can measure. For example, boulders we can measure number of boulders, we can measure size of boulders, we can measure their strength, their abrasiveness, we can measure hydraulic conductivity, we can determine if soils are contaminated or not, groundwater is contaminated or not. Okay, and then we can determine soil mineralogy, rock mineralogy, slake durability, permeability, if presence or absence of gas contamination. Okay, and so all those constitute physical baselines, and then we can provide percentage of ground types at shaft location and along the tunnel. Okay, and then we can show them that okay, what type of grounds we have. It is mix of different strata, interlayered soil or rock, soil mixture, rock mixture. So we can provide all those baselines, and those are physical baselines. These can be measured and can be quantified. Behavioral baselines, it is basically behavior of the ground during tunneling. Okay, so for example, if we are in saturated gravel and if we use open face microtunneling boring machine, then the saturated gravel will flow into it. Okay, so this is a behavior. So gravel will not flow if you don't excavate, but when it is if it is confined, it will not flow. But when it is unconfined, you excavate and there is an open face, then it will flow. While in closed face microtunneling machines, that's not the case because the face will support it. So there is a very good document, Tunnelman's classification system, that provides behavioral aspects of different grounds. And for example, firm, raveling, running, flowing, squeezing, those are different behaviors of the ground when the ground is unsupported. Blockages, for example, if you are in claystone, and claystone in its in situ state may not be sticky, it may be dry, but when during tunneling we add water to it, it becomes sticky and it will clog cutter head and conveyance system. Okay, so for example, this is state of the art paper which basically tells you about clogging. So for example, if your soil, clay or clay till or claystone is in this zone, then basically it is not clogging, but when you add moisture into it, it will after some point it will become a strong clogging. It will have strong clogging potential, and you add more water, it will disperse and clogging will disappear. Okay, so if you are in this type of ground, your machine should be equipped with unclogging system. So this is a behavior. Okay, so these are behavioral baselines. Few of them I discussed. So for claystone, the other behaviors are that when they are exposed, it will disintegrate. It will swell when it becomes wet. So, and it will clog. If you add water to it, it will become sticky. All those behaviors. Similarly, bedrock in Calgary is a sedimentary rock, and it is in horizontal to subhorizontal layers. And if you excavate through it, and if the roof of the tunnel is not supported, the layers will fall down, and that is called slabbing. That is another behavior, that if you don't support it, it will fall down. So we have to provide behavioral baselines as well. There are some reference documents which are very good as guideline for preparation of geotechnical baseline reports, and also um, how much geotechnical investigation, hydrogeological investigation, environmental we have to do. So those are reference documents if you are interested in reading them. There are some other documents that I have referenced. They provide some guideline as well, how much geotechnical investigation should be done. The nutshell is that if you spend more money on a site investigation, cost of risk will reduce. Okay, so that is the nutshell, and you have to see how much investigation you have to do. So what type of investigations are required for preparing geotechnical baseline report? So first of all, it is a desktop study. So we have to review geological maps of the area, existing geotechnical reports, existing geotechnical baseline reports for other projects, as built information for other projects, similar projects, okay? Information on tunnels in the area in similar ground conditions, tunneling issues, what were the means and methods, and what were the machines they used. That all provides very good information. Then after that, so this desktop also help you in selecting a drilling method for geotechnical investigation. So then you do geotechnical investigation, and based on a review of all those documents, normally we drill boreholes at 90 meters spacing and test holes to extend minimum 2 times the tunnel diameter below the tunnel invert. Geophysical investigations, we normally do them when we are in hard rock, and rocks have fractures, beddings, and joints, and folds and faults. So with geophysical investigation, we can map that. Then we can do hydrogeological investigation, and with that, we measure hydraulic conductivity of soils, pumping test to determine flow rates, and then we do packer testing to determine hydraulic conductivity of rock. Environmental investigations are done to confirm if the soils are contaminated or not, because if they are contaminated, they have different disposal requirements. And after that, we have to do laboratory testing, and those are specific to projects. But in Calgary, for tunneling projects that I have done, we have done these type of tests: moisture content, Atterberg limits, particle size distribution, and that is for soils. Okay. Atterberg limits we also do for claystone. Direct shear for soils and bedrock. Uniaxial compressive strength. Normally we do it for rock. Swell test for claystone. Slake durability for claystone. Searcher abrasivity for sandstone and boulders. X-ray diffraction for claystone, and electrochemical tests for soils and bedrock to see what is their pH, resistivity, chlorides, and sulfates. Sometimes we do in situ tests for rock as well, such as pressure meter. So once the investigations are completed, then we have to prepare different reports. So first one is geotechnical data report, then hydrogeological data report, then environmental data report. So all these three reports, they provide only data, no interpretation, no recommendation. And after that, we have to provide geotechnical baseline report. And geotechnical baseline report doesn't have any borehole logs, because borehole logs are in the data reports. No lab test results, because lab test results are in data reports. Then we provide anticipated ground conditions and baselines. Anticipated means we don't have to rely only on this investigation. We have to rely on the desktop study that we have completed. Okay. Then in a geotechnical baseline report, we don't provide any recommendation. We only provide baselines on means and methods. Sorry, we don't provide recommendations, and we don't provide any baselines for means and methods. That is contractor's responsibility. We provide baselines for ground conditions, and contractor has to select equipment based on those baselines. And remember, baselines must be quantitative, that can be measured or quantified. Okay, qualitative baselines are not acceptable. And most important, 3 C's. Okay, baseline report should be clear, concise, and consistent with other documents. Okay, when we say other documents, means specifications, so they shouldn't contradict each other. Now we will discuss Englewood sanitary trunk, what ground conditions were encountered, and what baselines we have provided. So first of all, this figure shows how many boreholes we drilled. So all those circles, they show boreholes. Basically, we drill boreholes at 90-meter spacing, and all boreholes extended at least 2 times tunnel diameter below the inward elevation of the tunnel. And we installed monitoring wells in all of them to measure hydraulic conductivity, and then we did some pumping tests as well. So you can see these are the ground conditions that we encountered. So the different colors, and I'll explain what those colors are. So this gray color is bedrock, and bedrock, as I said, it is sedimentary, and it has 3 components: claystone, siltstone, and sandstone. So remember, claystone has clogging potential. It is extremely weak. It swells when it becomes wet, and it disintegrates when it is exposed to weather. Then sandstone and siltstone, they are strong, which means they can have strength as high as 150 MPa. And then they are very abrasive. So you see both rocks have different characteristics and behaviors. This light brown or beige color, this is coarse granular soil unit, which means it is sand and gravel, and it contains cobbles and boulders. And it is, if you see the tunnel, this red line is tunnel, this green line is tunnel. So the tunnel is underwater. If you see, it is underwater. This yellow is um, fine granular soil unit, which means it is sand, silty sand or sandy silt. Okay, so both these soils, coarse granular soils and fine granular soils, they will flow into open face a microtunneling machine. This is their behavior. Okay. Similarly, this light green color, this is silt or clay, and both of them have clogging potential. And this dark green color, this is clay till, cohesive glacial till. So it has clogging potential, and it has cobbles and boulders in it. So if you can see from here, so let me plot something. So if you can see here, the tunnel is in claystone. And if you see here, it transitions from claystone into coarse granular soil unit, and then it is all in coarse granular soil unit. In the next slide, the next tunnel section, it is all in coarse granular soil unit. Next tunnel is in coarse granular soil unit, and then it transitions into bedrock. Okay, so you can see this contact point. Then the tunnel enters into a buried channel. And then if you go further, the tunnel is again in bedrock. Next slide, bedrock again transitions into clay till, from bedrock to clay till, then clay till into bedrock, bedrock into clay till, and then again this contact point. So these contacts are very important. We have to provide baselines for this contact point, okay? Because this contact point is interpreted. We have information at the borehole locations. We don't have information in between boreholes. So we have interpreted this. So this contact is interpreted. So this can This contact can be here or it can be here. Okay, so we have to, and similarly in vertical direction, it can be here and it can be here. So we have to provide a baseline for that contact as well. And then in the next figure, you can see we are in tunnel is in bedrock, and then it transitions into coarse granular soil unit. So you see, ground conditions are highly variable, okay, along the tunnel, and each soil and bedrock unit has different characteristics. It is very difficult ground, so we have to provide baselines for those difficult ground conditions. And one thing you should remember, that coarse granular soil unit uh, and groundwater is above tunnel. So it is, you cannot basically do open face tunneling in this soil. So the first baseline that you have to provide is the percentage of each soil unit along the tunnel alignment. So our baseline was that the tunnel alignment has 48% coarse granular soils, 8% clay till, and 44% of bedrock, which is a mixture of clay stone, siltstone, and sandstone. And this is for phase one. For phase two, we have provided similar baselines. So remember, phase one has been completed. Phase two is still under progress. So design is under progress, not construction. Then for those contact points that we discussed, we provided baselines for in vertical direction and baselines in horizontal directions. What did we say? The contact between different soil units and soil and bedrock units shall be assumed to vary by plus minus 3 meter vertically and plus minus 50 meter horizontally at any point. Okay, so two baselines. Then we provide baselines, physical baselines for soil. So, and that first one is the gradation envelope, and this gradation envelope is for coarse granular soil unit. You will see how important this is when we go further into this presentation. And then we have to provide histogram distribution of SPT N values, which tells us that how compact is this soil unit. So we have to provide similar gradation envelopes and histogram distributions for other soil units. Then we know that clay has clogging potential, and we have assessed based on Etterberg limits and that chart that I have shown you before. And we found that clay stone, not clay stone, clay and clay till, they have strong clogging potential. Okay. Now, when we provide this baseline, contractor have to equip his machine with equipment, unclogging equipment. Okay. So that will be different polymers and I mean adding water and all those things. Then boulders, we have to provide a number of boulders, size of boulders. We have to provide unconfined compressive strength of boulders. Like here we have provided average UCS of 260 and maximum 380. This is very strong boulder, okay? And we have provided abrasivity index of 4.9. Just so that you know, a maximum abrasivity index is 5, which means these boulders are extremely abrasive. Then we have to provide baselines for groundwater inflow rates into tunnel and shaft if they are not lined and if they are not sealed. Okay. So you see, for example, in this tunnel section, the groundwater inflow rate is 9,000 liters per minute per meter, which is very high, and it is not practical to dewater. Okay. Similarly, you can see at shaft location, the groundwater inflow rates are very high. What does that mean? That means that dewatering is not feasible. Soil quality. So we have to provide a baseline if the soils are contaminated or not contaminated, because contaminated soils have different disposal requirements. Similarly, groundwater, it is contaminated or not, it has different disposable requirements. So we said soils are not contaminated and groundwater is not contaminated. So during construction, if it is contaminated, then it is then the cost who will bear the cost? City of Calgary will bear the cost. Combustible gases, we said the soils are non-gassy, which means there are no gases, okay, in the soil and bedrock. Then we will provide behavioral baselines for soils, and this is from tunnel man classification. So we have to provide the behavior of clays, silty clay. We have to provide behavior of clay till, that it has strong clogging potential, and how it will behave if it is not supported. Gravel and all those things. Gravel, sandy gravel, gravel and sand and gravel, basically, which is coarse granular soil unit, how that will behave against unsupported vertical face. A fine granular soil unit and bedrock. And we have discussed slag durability. We have discussed swelling potential, and we have discussed slabbing. So those are all behaviors. Then we have to provide physical baselines for bedrock. So one of the most important thing is unconfined compressive strength, and we baseline 90 MPa for sandstone. And we don't say sandstone, we say for bedrock. Clogging potential for claystone, strong clogging potential. Slag durability, claystone has very low slag durability, which means when it is exposed to weather, it will disintegrate. Abrasiveness for sandstone, we provide 1.92. Then we provided baselines for each tunnel section, and we provided baselines for each shaft. So after providing all those baselines, we went one step further, because we know the ground is very challenging. Open face machine is not suitable. Dewatering is not practical. So we specified few things. So those were not baselines. These things were in the specifications. So we said contractor should use pressurized close phase MTBM. And then he can use either slurry or earth pressure balance machine, but it must be pressurized close phase. Shafts must be sealed so that there is no dewatering, okay? And then we said dewatering for the purpose of lowering groundwater level is not permitted. Because if we do dewatering, first of all, it is not practical, but even if it is practical, there is potential that because of excessive dewatering, there will be impacts on adjacent infrastructure, and we don't want to do that. And then we said soil and groundwater are not contaminated. However, testing of soils and groundwater is required prior to disposal. Then we will see what we encountered during construction. So as we specified, contractor used pressurized closed face slurry type MTBM, and contractor used shield method of shaft construction, and which was basically caisson sinking. So during construction, what happened, that contractor informed us that there is something wrong with the tunnel boring machine. So they have to do an emergency intervention, which means a rescue shaft, and expose the tunnel face and see what is wrong. So they exposed it, and they found that the cutting tools are damaged. Okay, so they are damaged because they encountered hard ground. So what is hard ground? Because at that location, tunnel was in coarse granular soil unit. So that soil unit has boulders. So they submitted a claim, and for that claim, now we have to collect some information to see if that claim is valid or not. If, for example, if our baselines are not correct, or boulders that they encounter are more aggressive, then we have to pay them that claim. But if not, then we have to reject that claim. So what we did, that we collected boulders from this rescue shaft. We counted them, we measured their sizes, we did unconfined compressive strength tests, we did abrasiveness tests, okay? And then we collected soil samples from coarse granular soil unit to see if this falls within the gradation envelope. So we did two gradation tests, and both of them were within the gradation envelope. So which means that on this side we are fine. So the next step was to measure the unconfined compressive strength of boulders. So we took 7 samples and we measured unconfined compressive strength, and minimum was 49 MPa, maximum was 249 MPa, and average was 142 MPa. We measured abrasiveness for 2 samples. One sample had abrasiveness of 1, and So the second one had 4.87 and our baseline was 4.9. So we were fine on this, we were fine here. So basically we rejected that claim. So you can see how useful is the geotechnical baseline report. Otherwise you will go into litigation, okay, and that takes long time. Projects are delayed and there are delay costs then, and that becomes a bigger problem. So to end my presentation, I would conclude that the GBR proved to be a very effective tool in resolving claims for differing ground conditions for this project. There were very fewer claims because contractor used means and methods most of the time consistent with the geotechnical baseline report. There were no delays and the project was completed within time and within schedule. So this concludes my presentation. I would like to thank City of Calgary, Ward and Burke Microtunneling, Earth Drilling Company, who were our sub for drilling the test holes. And at the end, I would like to thank AECOM Geotechnical and Design teams who provided support during design and construction of this project. So thank you for your patience. Any questions? And I have provided some data on this slide. So phase one construction cost was about $78 million. Phase two construction cost is expected to be around 19.3 million. Investigation cost, including all reports, was about 1.5 million. AECOM design fees were 5.6 million. Total claims that we paid were about $400,000 and total claims that we rejected were $1.1 million. So looking at the size of this project and cost, claims were nothing. So that is all because of geotechnical baseline report. Thanks. Any questions?